Hey guys, I wanted to start off by doing these first 4 problems and explaining how to balance chemical equations. So my general approach to this is to go throughout the entire reaction from left to right, making sure that there are the same number of atoms of each element on either side of the reaction arrow. If there aren't, I simply adjust the stoichiometric coefficients, and then once I get to the end, I circle back through from left to right and make sure everything checks out. So I'm just going to run through these and you'll see what I mean, okay? So the first compound on the reactant side here is FeS. So the first element there is iron. And I see that there is 1 iron. So just so we're all on the same page, if there's no number in front of the compound in a reaction, that means it's assumed to be 1. So even though there's no number written here, right now it's an invisible 1. So I've got 1 iron here and 2 irons here. So in order to adjust for that, I'm going to make that a 2, okay? So now we have 2 irons over here and 2 irons over here. So now let's go to the next atom, sulfur. That's the next element, so we have 2 of those, right, since we made this a 2. So we better have 2 over here. But look, we only have 1 sulfur over here. So I'll adjust by making that a 2 as well. So now we've got 2 irons, 2 sulfurs, 2 sulfurs, 2 irons. So now the irons and the sulfurs match, so now let's check oxygen. So oxygen, I see that there are 2 on the reactant side. So there must be 2 over here, but it looks like we've got way more than 2. So first of all, we've got 3 from this compound, and then actually 4 from this compound, because 2 SO2 is 4 oxygens, so 3 plus 4 is 7. So we've got 7 over here and 2 over here. So how do I make this into a 7? Well, I'm actually going to have to use a non-whole number, because 3.5 O2 is 7 oxygens. And we know we can't leave it like this, but we'll put it like that for now, and then when we circle back through and fix everything, we'll balance everything out. So right now, everything is actually balanced, right? We have 2 irons, 2 sulfurs, 2 irons, 2 sulfurs, 7 oxygens, and then 7 oxygens, right? But the problem is we can't leave this as a 3.5. We have to get this to a whole number. So what's the smallest whole number that I can get 3.5 to by multiplying it by some constant? Well, if I just multiply it by 2, I can make it into a 7. But this is like algebra. When we do something to one side, we have to do it to everything else. So I have to multiply everything else by 2 now. So now this 2 will turn into a 4. This invisible 1 will turn into a 2. And this 2 will turn into a 4. Okay, so now the reaction is totally balanced and we finished number 1. So that wasn't that bad. You just kind of have to go through atom by atom, adjusting as you go, and then check everything at the end. So let's move on to number 2 here. So the first compound, PCl5. So phosphorus, I see that there is 1 phosphorus on this side total. So there better be 1 phosphorus on this side total. And there is, right? There's just 1 here. So the phosphorus checks out, there's 1 on each side, so we'll move on. So now I see that there are 5 chlorines on this side total. So that means we must have 5 chlorines on this side total. Well, the only place I see a chlorine is here, and there's just 1, right? So I need to change this to a 5, at least temporarily. So now the chlorines are balanced. Okay, now let's move on to the next atom, hydrogen. So there are 2 hydrogens total over here, but there are 3 plus 5, so 8 total over here. So how do I get H2 to 8 hydrogens total? Well, if I put a 4 here, that fixes that. Right now we've got 8 hydrogens, so we'll leave that there for now, and then we'll move on to our next atom, oxygen. So 4 oxygens on this side. How many oxygens on this side? Well, just 4, right? That O4. So the oxygens check out. So we went through all the reactants and balanced them temporarily with all of our products. So let's circle back through and make sure everything still matches. So phosphorus, 1, 1, we're good there. Chlorines, 5 chlorines, 5 chlorines. Hydrogen, so we've got 4 times 2, 8 hydrogens. And then 3 hydrogens plus 5 hydrogens is 8 hydrogens, so we're good there. And then oxygen, 4 and 4, so we're good. So whenever we didn't have to change the stoichiometric coefficients, we know that they started as 1, so we can go ahead and write those in as 1 now because we know that's our final answer. Okay, moving on to number 3. So we've got C2H6O plus O2 goes to CO2 plus H2O. So let's start with the carbon. So we have 2 carbons on this side, 1 carbon on this side. So we'll change that by making this into a 2. So now there's 2 carbons, 2 carbons. Moving on to the next element, so 6 hydrogens, 2 hydrogens. So I'll make this into a 3 to make it 6 and 6. And then I'll move on to this oxygen. But we see oxygen also appears right here in our reactant side. So there are 3 total oxygens on our reactant side. And how many total oxygens are on the product side? Well, 2 CO2, this is 4 oxygens here, and then 3 oxygens here. So we actually have 7 oxygens over here. So we're going to have to do something similar to what we did in the first problem. So we have 7 oxygens over here, but O2 here, and then O here. So 3 and 7. So it's a little bit different in that we have 2 options here. We can either increase the amount of this oxygen or the amount of this oxygen. And we have a bit of an advantage because this will give us an odd number of oxygens. 2 plus 1 is already 3. So if I make this into a 6, 6 plus 1 is 7. So now we have it balanced. So notice how having this extra oxygen made it into an odd number, so we didn't have to use a decimal here. So now let's check, make sure everything is balanced. So 2 carbons, 2 carbons, 6 hydrogens, 6 hydrogens. 1 plus 6, 7 oxygens. 4 plus 3, 7 oxygens. So we're good. So I'll go ahead and add a 1 here for this coefficient. And then the last one here. So I'll start with magnesium. So there's 1 magnesium over here, 1 magnesium over here. So that's good. So OH with a subscript of 2. So this basically means magnesium bonded with 2 hydroxide groups. So this means we have 2 oxygens and 2 hydrogens, right? So 2 oxygens on this side, 1 oxygen on this side. So I'll make this into a 2 to get the 2 oxygens to match with these 2 oxygens. Then hydrogen. So I've got 2 hydrogens here plus 1 more here. So 3 hydrogens on this side, 4 hydrogens on this side. So how can we get this side to have 4 total hydrogens? Well, we've got 2 here, and then, well, we could just turn this into a 2, right? So 2 and 2, so 4 hydrogens now matches with 4 hydrogens. Okay, so let's circle back through and make sure everything matches. So 1 magnesium, 1 magnesium. So we're good there. 2 oxygens, 2 oxygens. 2 hydrogens plus 2 hydrogens, so 4 hydrogens. 4 hydrogens, so we're good there. And then 2 chlorines, 2 chlorines. So we're good. So we'll add in these as 1. So those are our final coefficients. So I hope that makes sense on how to balance chemical equations. Okay, so this next problem says that a 0.2 gram sample of a compound containing carbon, hydrogen, and nitrogen is combusted, producing 0.33 grams of carbon dioxide and 0.339 grams of water. And then we want to ask what percent by mass of the sample is made up by hydrogen. So the first thing I did here was I wrote out the chemical equation. So they told us that we had a compound containing carbon, hydrogen, and nitrogen. So I wrote out a generic compound with unknown subscripts here for the number of atoms, carbon, hydrogen, and nitrogen. These are all just variables because we don't actually know those numbers. And whenever you combust something, you add oxygen to it in the form of O2, and it turns into CO2 and water. So the first step here is to understand what do they mean by percent by mass of the sample being made up of hydrogen. So percent by mass of anything is just the mass of the thing you're interested in over the mass of the total sample. So in this case, the percent by mass of hydrogen is going to be the mass of hydrogen over the total mass of the sample, and then times 100 to get us a percentage, okay? So really what we need here is just the mass of hydrogen that's in this compound that we started with, because we already have the total mass of the sample, and then once we multiply that by 100, we'll get our percent by mass of hydrogen. So in order to figure this out, I use the principle that if we started out with a certain amount of hydrogen over here, we must have ended up with the same amount of hydrogen over here by mass. So for example, if I started out with 5 grams of hydrogen, yeah, all these atoms rearrange themselves into different compounds, but I'm still going to have 5 grams of hydrogen total, okay? So that's the principle that you have to use to solve this problem. So all they told us was that we had 0.339 grams of water and 0.330 grams of carbon dioxide. So notice we don't really care about the carbon dioxide because it doesn't have hydrogen in its formula. So this actually turns out to be unnecessary information that they gave us just to throw us off. And water here contains the hydrogen, and they told us the total amount. So how can we get the amount of this total mass that was made up by hydrogen? Well, ironically, we have to use the percent by mass of hydrogen over here. So we know that the total mass of the water was 0.339 grams, but a percentage of that by mass is going to be made up of hydrogen. So if we can figure out what that is, and we can do that fairly easily, we could just multiply 0.339 grams total times the percent by mass of hydrogen in water, and we'll get essentially the mass of hydrogen in that sample of water. So you can figure out the percent by mass of hydrogen in water by simply saying each hydrogen is going to weigh 1.008 grams per mole from the periodic table, and we have 2 of those. So 1.008 times 2 over 18 grams per mole, which is the total weight of water, of 1 mole of water. So this will be your percent by mass of hydrogen in water. You can do that for any compound. Simply have to find the periodic table molecular weights. So then we'll say 0.339 times that percentage is going to give us the mass of hydrogen in this sample of water. So 0.339 grams times 11.2%, which is what this came out to be, gives us 0.038 grams of hydrogen. So since we ended up with 0.038 grams of hydrogen, we must have began with 0.038 grams of hydrogen. So now we have our numerator here that we wanted. So 0.038 grams over 0.2 grams is the percent by mass of hydrogen. So 0.19, when you multiply that by 100, you get 19%. So that's our answer here. Our original sample was 19% hydrogen by mass. Okay, this problem is an empirical formula problem. So they say an 8.77 gram sample of hydrocarbon was combusted completely, producing 28.5 grams of CO2. And then they ask, what is the sample's empirical formula? So the first thing you have to understand here is what an empirical formula actually is. So an empirical formula is essentially the lowest whole number ratio of atoms to atoms within a compound. So let me show you an example. So for example, our compound here is CH. So an example for an empirical formula could be C2H5, right? That would mean 2 carbon atoms for every 5 hydrogen atoms. And that would be an empirical formula because 2 to 5 is the lowest whole number ratio of 2 to 5. You know, you can't reduce 2 over 5 as a fraction. So that would be an empirical formula as an example. And they say that this was combusted. So I went ahead and wrote out the reaction here. So our hydrocarbon plus oxygen gas goes to CO2 and water. You know, that's what happens in a combustion reaction. And then they give us the masses of our hydrocarbon and the CO2 produced. So we need to figure out how to use those. Well, I wrote out a general method, step-by-step method that you use for empirical formula problems. So step 1 is we have to get the gram amounts of the atoms in our compound to moles. And then step 2, we need to figure out the lowest whole number of the molar ratios. And that'll make more sense when we get there. But for now, I want to figure out how many, first of all, we need grams, right? We need grams of carbon and hydrogen from our initial sample. And we're going to have to use the same principle we used last problem. And that is that the amount of carbon that we started with in mass has to be equal to the amount of carbon we ended up with. Even though the atoms were rearranged and made into different compounds, we still had the same amount of carbon in mass. And the same holds true for hydrogen. So they told us that 28.5 grams of CO2 were produced, right? And that's our only source of carbon in the product side. So if we simply take the mass of CO2 and then figure out what percentage of it is made up of pure carbon, we can figure out the total pure carbon that was produced. So the percent by mass of carbon in CO2 is the molecular weight of carbon over the molecular weight of CO2, and you can find that on the periodic table. We'll multiply that by the total mass of CO2, and you should get 28.5 times 0.273, and that gives you 7.78 grams of carbon, which were produced. So that means that we started out with 7.78 grams of carbon. Now we can figure out hydrogen fairly easily because they told us that the sample initially weighed 8.77 grams. So that means 8.77 grams minus the amount of carbon weight equals the hydrogen weight, because it's only made up of carbon and hydrogen. When they say hydrocarbon, that just means made up of hydrogen and carbon, right? So now we have grams. So now step one is to get these gram amounts to moles. So we'll take 7.78 grams of carbon and convert that to moles of carbon using this table here. So we leave the units that we want to leave on bottom. So we'll cancel out grams of carbon, and we want to go to moles of carbon. So we'll put this on top. So grams of carbon cancel out, and you do 7.78 divided by 12.01, and you end up with moles of carbon, and this is 0.65 moles. So we'll do the same thing with hydrogen. Remember, we're on step one here. So 0.99 grams of hydrogen, and we'll put grams of hydrogen on bottom because we want to cancel that unit out. And so we'll do 0.99 over 1.008, and we'll end up with moles of hydrogen. So this will be 0.99 over 1.008, and we get 0.98 moles of hydrogen. So step two now, we need to figure out the molar ratios. And to do this, what you do is you divide by the lowest number of moles. So you divide everything. You know, we could have more than two elements here. We happen to have two this time. So we'll divide both of these numbers, 0.65 and 0.98, by the lowest number, 0.65. So when you do that, you're going to get 1 here, obviously. Anything divided by itself is 1. And then for this one, you're going to get 1.5. So what this means is that for every 1 carbon atom, we have 1.5 hydrogen atoms. Or for every 1 mole of carbon, we have 1.5 moles of hydrogen. So what we have to do now is make sure that these are both whole numbers, right? An empirical formula, part of the definition is that it is a whole number ratio. So we need to find the lowest number that we can multiply this non-whole number by to make it into a whole number. Well, luckily this one's pretty easy. 1.5 times 2 is going to give us a whole number, 3. But whatever we do to one of these numbers, we have to do to all of them. So this will be 2 and 3, and now they're both whole numbers. So your empirical formula here would be C2H3. So this is actually not a real compound. You're not going to find that in nature, but this strategy is going to work for all of these empirical formula problems, so I hope that made sense. Now we get to a stoichiometry problem. So I know this stuff looks scary, but it's really not that bad, and you guys really need to learn this well now, because I promise you this will come back to haunt you. Learn it well now and you'll be well off for the rest of your college career, because this comes up in Chem 2, biochem, other biology courses, so it's really important. So I have a reaction here. 4FeS plus 7O2 goes to 2Fe2O3 plus 4SO2. So this is how a general chemical equation is written, right? With these numbers in front of each compound. These are known as the stoichiometric coefficients, and they basically tell you that 4 moles of this reacts with 7 moles of this to make 2 moles of this and 4 moles of this. It eliminates the need to know how much anything weighs. It tells you, because moles are a counting unit, it says a certain number of these react with a certain number of these to make a certain number of this and this. And stoichiometry is essentially the conversion between moles and grams among all of these compounds. And so this is the general directional flow that these problems take. You may start with grams and you have to get moles. You may start with grams, but you have to get moles of something else, and you'll have to go from here to here to here. You may start with grams of one thing and have to get grams of something else, and then for this you have to cross what's called often the mole bridge. So grams to moles to moles to grams. So you'll see how this fits into these problems here. So these are some very common types of problems that you may be asked. So how many moles of FeS are required to react with 12.58 moles of O2? So what information are we given to begin with? Well, you always take the number that they give you, 12.58 moles of O2, and you put that on the top left of your table. So we put that up here, and then we have to think about, okay, we're at moles, and we want to get to moles, right? So we just have to take one step. We don't have to go to grams, we're already at moles, so we go one step, and we want to go to moles of FeS, right? That's what they're asking for. And whatever you have up here, you have to have the same units down here to cancel them out and leave these units behind. So we'll cancel out moles of O2, and we'll go to moles of FeS. And we know that for every mole of FeS, for every 4 moles of FeS, there are 7 moles of O2. So that's where this 4 and the 7 come from. So when you do this on your calculator, you'll do 12.58 times 4, then divide that number by 7, and you should get 7.19 moles of FeS. Okay, let's look at the next one. So how many moles of Fe2O3 are produced from 9.47 moles of O2? So this is the number we were given, so we'll start with that on our top left of our table. 9.47 moles of O2, and what are we going to? We're going to moles of Fe2O3, right? So again, we're just taking this one step here from moles to moles, so we don't have to worry about grams. We have to cancel out these moles of O2 down here, and then we're going to moles of Fe2O3, and we know that for every 2 moles of Fe2O3, there are 7 moles of O2. So we'll do 9.47 times 2, and then divide that number by 7. You'll get 2.71 moles of Fe2O3. Okay, how many moles of O2 are required to completely react with 33.5 grams of FeS? Okay, so here we're asked about moles, and then we're given information in grams. So here it could be a one-step problem if we're dealing with the same compound, but we're dealing with O2 and FeS. So what we're going to have to do here is go from grams to moles to grams. We're going to have to do the entire length of this directional path here. So how many moles of O2 are required to completely react with this? So this is the information we're given. We'll put that in the top left here. So 33.5 grams of FeS. And we know to cancel out these units, we have to have grams of FeS down here. And we're trying to get to moles of FeS, right? Because we started in grams, we have to first get to moles. So now we're in moles of FeS, and we have to cancel this out again down here. And ultimately, we wanted to get to moles of O2. And we know that for every 7 moles of O2, there are 4 moles of FeS, right? And by the way, this is the molecular weight of FeS from the periodic table. This is how you get, in general, from grams to moles. You take grams up here, cross out the grams down here, and you go to moles up here, and then you get the molecular weight off the periodic table. So notice in that problem, they actually asked for moles, and we started with grams. So really, we started here, we started with grams, then we went to moles right here, and then we went to moles here. So we really only had to go from here to here to here. So if they had asked for grams of O2 at the end, we would have had to go here, 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 and then here. It would have been a 4th step. And we'll see one like that. But let's do number 4 now. So how many moles of SO2 are produced from 96 grams of FeS? So again, we'll start with what they gave us. FeS, 96 grams, up in the top left of our table. We know the units down here are going to have to be the same as this to cancel it out. And we're trying to get to moles of FeS up top, because here we have 96 grams, so we're going from grams of FeS to moles of something else. So this is very similar to the last problem. We're starting with grams of something, we have to go to moles of that thing, and then we'll get to the moles of the other thing. So 96 grams of FeS, we'll cancel out grams of FeS down here, we'll get the molecular weight off the periodic table, we already had that from the last problem, and then we'll end up with moles of FeS after that. So then we have to cancel out moles of FeS down here, and we want to end up in moles of SO2. And we know that for every 4 moles of SO2, there are 4 moles of FeS. So 4 and 4, so you'll do this times this times this, divided by the product of these two, or this times this, and you end up with 1.09 moles of SO2. So number 5 here, so how many grams of Fe2O3 are produced with 48 grams of O2? So here is an example where we really have to go the entire length of this directional flow. We're starting with grams of one thing going to grams of something else, right? So we're going to have to go from grams of grams of oxygen, which is what we were given. We'll start with that on our top left here. And then we have to go to moles of oxygen. Then we'll go to moles of Fe2O3, and then finally grams of Fe2O3. So that's the general scheme, but let's walk through it. So we start out with 48 grams of O2, and we know we're going to get to moles of O2, and we have to cancel out grams of O2, these units down here. We know that there are 32 grams of O2 for every 1 mole of O2. Then we'll go to moles of Fe2O3. So we got to cancel out moles of O2 down here, and we know that for every 2 moles of Fe2O3, there are 7 moles of O2. And then we have to cancel out this moles of Fe2O3 down here, and we'll finally end up with grams of Fe2O3. So this is converting from this final moles to grams. So we'll get 159.7 grams of Fe2O3 per 1 mole of Fe2O3. We just get this off the periodic table, and you should end up with, when you multiply the entire numerators divided by all the denominators multiplied together. So in other words, I would multiply this times this times this times this, save that number, multiply this times this times this, and then that saved number divided by this number should give me 68.44 grams of Fe2O3. So this is a fairly confusing topic, especially for the first time. So don't feel bad if it's confusing. You really just have to practice, practice, practice. And please let me know if there's any questions that you have or anything else you'd like to see. Okay, so this is the last problem I want to go through for this video. So they tell us that 63 grams of C2H4 are combusted completely with O2 to produce CO2 and H2O, as all combustion reactions do. And they ask what mass of CO2 is produced. So I wrote out the equation up here, the chemical equation. So we've got C2H4 reacting with O2 to make CO2 and H2O. And for this problem, it doesn't really matter that if it's balanced or not. I didn't even check. But what is important to note here is that this same concept that we've been hitting on, you know, the amount of carbon mass that I begin with is going to be equal to the carbon mass that I end with. And I'm going to use that principle to my advantage. So they give us an initial mass of the C2H4, and we know that the carbon of that C2H4 is going to be equivalent to the carbon of the CO2. So let's figure out how much carbon is in 63 grams of C2H4. So the grams of carbon in 63 grams of C2H4 is simply going to be the total weight, 63 grams, times the percent by mass of carbon in C2H4. So 63 grams, and then we'll multiply that by the percent by mass of carbon in C2H4, which is 2 C's, so, you know, because there's 2 carbons, 12.02 times 2 over 28.05, and when you multiply this out on your calculator, you should get 53.95 grams of carbon. So that means that 53.95 grams of carbon started out here and they ended up here, right? It says it was completely combusted. So that means there must be 53.95 grams of carbon in the CO2, right? So we know that 53.95 grams of carbon from the C2H4 is all going to be part of this carbon in the CO2. So we'll set that equal to the total mass of CO2 times just the percent by mass of the carbon in the CO2, right? Because this only makes up the carbon of the total mass. So you say total mass times the percentage that's made up by just the carbon, because that's what this is. So then we say 53.95 is equal to the total CO2 mass times the percent by mass of carbon in CO2. So we'll say 12.01 for the 1 carbon over 44.01 for the total mass of CO2. And then we'll divide both sides by that percent by mass. So these will cancel out, and then you'll get 53.95 over that percent by mass of carbon in CO2. And when you put that into your calculator, you should get that 197.6 grams of CO2 were produced. So please let me know if there are any questions about that. I really hope this first lecture helped you guys. Please give me feedback and feel free to contact me. And thanks a lot and good luck.